we want to show that there's no such function that from positive number to real number, such that f of x plus y is always greater than y times f of x quantity squared for all xy that's greater than 0. So before I actually start solving this problem, the blueprint is that first I'd like to show that f of x is bounded over some fixed interval from 0 to some fixed positive number. Then I'm going to show that f of x is somehow unbounded, so which leads to a contradiction. So I can prove there's no such function. So first of all, if I let x and y equal to half of x, then immediately I have f of x is greater than half of x times this thing squared. So obviously greater than 0 for all x that's positive. Then I want to have a look at in this interval 0 to a, right, for some positive a, and I'll let x be x and y be 2a minus x. Right. Here's y. Because now I can say that f of x plus y, that is f of 2a, is greater than y times f of x squared. Because here's a, here's 2a. X is somewhere here. And the reason I use 2a is because now I can say that 2a minus x, worst case scenario, is going to be a. Otherwise, it's going to be greater than a, obviously. Right? So greater than or equal to a times f of x squared. So in fact, here you can use 3a, 4a, doesn't matter. Right? The point is that eventually I reach some positive times some positive. So immediately f of x squared is less than or equal to f of 2a over a. Right? So because f of x is always positive, so here is some positive number. So f of x is always bounded above over any fixed interval, 0 to some positive fixed number. Right? Like I said, next I'm going to show that somehow f of x is actually unbounded, right, over some fixed interval, 0 to c, whatever. So I can reach a contradiction. So to construct a infinite sequence, I'll let xn minus 1 equal to xn plus 2 over f of xn. And I'll let x naught equal to some positive number, maybe 1, right? Doesn't matter. So the reason I construct it in this way, you will see why. Okay, you will see, is because this time I let x equal to xn, y equal to 2 over f of xn. So this time I can have f of x plus y, that is x plus y, that is f of xn plus 1 is greater than y times, so y times f of xn squared. That is simplified. 2 times f of xn. Right. So here, in fact, you can use 3, 4, 5, doesn't matter. Right. So the whole point is that now I can have, so since f of xn plus 1 is greater than this, so change the subscript, which means f of xn should be greater than, so copy down this 2. Should be greater than 2 times f of xn minus 1. So greater than, so 2 to the power of 2, right? Next is 2 to the power of 3 times f of x n minus 2. Right? So if it's 2 to the power of n plus 1 times f of x n n minus n x naught. Yeah. So which means f of xn plus 1 actually grows to infinity as n grows to infinity. Right? As long as I can show that x n plus 1 is really sitting in some closed fixed interval, 0 to some fixed positive c, whatever, right, then that's contradiction to this result. So how do I know that? So here, since f of xn is greater than this bit, so which means f of xn is in fact greater than 2 to the power of n times f of x naught. Right? So if I replace this with this in here, right? So this is greater than that. So this must be smaller than, right? So xn smaller than xn, 2 over, right? This bit, 2 to n f x naught. Okay. So smaller, first I copy this down. 2 to the n f x. Perhaps this can be simplified with this, n minus 1. Right. So this can be must be less than that. So same likewise, if I change the subscript right here, becomes n. So xn must be smaller than xn minus 1 plus 1 over 2 to the n minus 2 f x naught. So I do the same thing to this one. Smaller than, right, replace this subscript with this subscript. So x n minus 2 plus 1 over 2 to the n minus 3 f x naught. I copy down this and that. 1 over 2 to the n minus 2 f x naught plus 1 over 2 to the n minus 1 f x naught. Right, so f x common factor here. Right. So if it's minus 2, then it's minus 3, minus 2, minus 1. So if I say 2 replaced with n minus 1, so n minus 1, so x1. Right. So this is 1 unit greater than that, n minus n. So first of all, common factor. Right. 1 over 2 to the 0, so 1. 1. Next is half. Next is 2 to the 2. Last bit, 2 to the n minus 1. So here we have a geometric series. Right? Common ratio is half. So you have how many terms? 1, 2, 3, n terms. So 1 minus half. So 2 f x naught 1 minus half to the power of n. So which is less than, right? You get rid of this term. It becomes loosened. x1 plus half 2 over x fx naught. Right? So maybe x1 is what? x1 is x naught plus 2 over fx naught. There's another one. So 4 over fx naught. Right? Denoted as c. Right? Obviously positive. Because I said x naught equal to 1. Right? You can use mathematical induction. Easy to see that this is easy for us to see that xn all is always positive, right? Using mathematical induction, easy. Right, so therefore, over this interval, 0 to c. Of course, c is greater than x naught. Right? X naught is somewhere here. But anyway, so it doesn't matter what n is, natural number. Xn is always bounded above. Xn is always sitting in this, right? Always less than c, always in this interval. Right? Here, there, x naught, x1, x2, it doesn't matter. And also, how come fx as n grows to infinity? Definitely it grows, right? Grows to infinity. Fx definitely grows to infinity. Then how come can it be bounded above, over this interval, right? Here I just replace a with c, right? There is a, but here we have c, right? So it's bounded above by f of 2c over c, right? Which is still a constant. Right, bounded above here. How come it can grow to infinity, right? As n grows to infinity. So that's a contradiction. So there's really no such function.